With the SDG Sustainable Development Goals developed in recent years, the world is now striving for more sustainable and eco-friendly structures that can both protect the environment and create a healthy learning environment for the students. Today, we are going to present our ideas about a self-sustainable school building that reduces waste and provides a healthy learning environment.
In this section, we will discuss minimizing environmental impact, including building materials, energy efficiency, and water conservation. Due to temperature changes, stress, and weathering, cracks appear in concrete. Water and oxygen enter the structure, leading to corrosion and weakens the building. We solve this using self-healing cement. Cracks form in concrete, and when water reacts with it, forms a highly alkaline environment. Inside, Bacillus bacteria, which thrive in high alkaline, are stored in capsules with their food, calcium lactate. These bacteria remain inactive until water seeps in the cracks. Once activated, the bacteria consume calcium lactate and produces limestone, sealing the cracks. It reduces costly repairs and material waste. Most of the foundations of our school will be built using self-healing cement.
To maximize free solar energy, we've installed perovskite solar cells on our roof. Unlike traditional materials, perovskite, a mineral or a group of minerals with a unique crystal structure, can absorb light better and is more efficient, flexible, and cost-effective. Using a method called spin coating, we applied perovskite solution to a conductive glass slide, then span it to spread it evenly, then heated it to form perovskite layer. This process is simple and waste-free. However, a key concern was the lead toxicity in the standard perovskite solution, NaPbI3. To solve this, I've replaced it with MaGeI3, a non-toxic, stable alternative with nearly identical performance. Now we can harness solar energy efficiently and safely. First of all, why sand? Sand is an ideal material for thermal energy storage due to its high heat capacity. It can withstand temperatures of 500 to 1000 degrees Celsius, far more than traditional materials like water, making it perfect for long-term energy storage. Now I'll explain how it works. Excess electricity from PSC, perovskite solar cells, heats the sand inside an insulated container using a temperature-resistant wires. The heat is then transferred to a system that produces steam, which drives steam turbines. Sand batteries are essential for long-term energy storage and can be released to store heat during unexpected incidents.
Piezoelectric floors convert mechanical energy from footsteps into electrical energy with piezoelectric materials. They absorb pressure from walking or other movements, generating an electrical charge. We will install these floors in entrances, basketball courts, and staircases of our school, using the energy as backup energy for future use. We also use smart glass, which uses electrochromic materials. When a current is passed through the glass, it triggers a reaction in the glass, making it dark. A baseline current is always applied to the glass, making it slightly tinted yet transparent. When solar sensors detect less sunlight, it decreases the current, making it more transparent. When it detects excessive sunlight, more current is provided, making it more tinted and making the interior of the building cooler. Traditional heat regulation methods like ACs have high CO2 emissions, inefficiency, and costly repair. We deal with this using a chilled beam system, which has metal beams installed in ceilings connected to a network of pipes where water flows through, cooling the beams, which cools the surrounding air and creates air circulation. The cold surface of the beam radiates heat from the air. Humidity sensors are installed in the system, allowing the machine to use only enough energy to chill the room. We have two chilled beam systems. First, an aquifer system. Neutral temperature groundwater is extracted and distributed over 3 buildings. In summer, The water after passing through the school gets hot and is stored in the hot reservoir. In winter, hot water gets extracted from the hot reservoir, becoming cold water after passing buildings and gets stored in a cold reservoir. The cold reservoir can then be used to cool hot buildings in summer. The second chilled beam system is the aquaponics system. This is the aquaponics system of our school. Fish are housed in a tank. They produce waste, ammonia. The ammonia-filled water is hazardous to the fish, so it is transferred to a bacteria tank that converts ammonia into nitrates, a fertilizer for plants. The nitrate-filled water is pumped to a plant bed, which uses the nitrates inside, leaving the water clean again and pumped back to the fish tank. The cycle continues repeatedly. Here's also where we get food for lunch from plants and fish. The three components are placed around the school to maximize water circulation to cool the school. The waste system. The school lunch waste is given to worm and fly farms. The worm farms converts the waste into plant fertilizers, and the flies feed on the waste, hatching fly eggs which are consumed by fish in the tank. Another part of our waste system is seed recycling bins, collecting seed from fruit, regrowing them at the plant beds or other gardens to be consumed in the future. To minimize paper waste, most paperwork will be digital.
Although the water resources are hard to get in some places, there are still places that the savings are usually being easily overlooked. For example, schools and some places with populations. That's why adding an effective water reservation system is extremely important. To resolve that, permeable bricks allow water to pass through their surface instead of running off. They have porous materials which let water directly into an underground filtration and storage system. This reduces flooding and prevents pollution. The benefits are reduced flooding and prevents erosion to the pipes. Also, it is cheap to install and reduce burdens to the drainage systems, reduce urban heat island effect, irrigation to soil and gardens. These advantages are weed and growth and pests, and it may not endure a highly weight from vehicles daily. Also, it may not be able to function in extreme weather, like freezing temperatures, because water trapped in the pores of permeable bricks can freeze and expand, leading to cracking and surface damage.
Our school's curved buildings are designed to maximize natural sunlight, creating warm and well-lit classrooms that encourage students' mood and well-being. It also allows more convenient circulation as students from different departments can go to and from easily. Surrounded by greeneries, one building features an indoor garden, while two others feature sky gardens, offering students a space to relax, connect with nature, and engage in open discussions. A highlight of the campus is the public access park, which includes an aquarium, which is also a part of an aquaponics system. This multifunctional space serves as both marine biology hub and a hands-on experience for both students and visitors. The interconnected buildings and varied designs encourage movement, promoting students' health. Additionally, to install environmental responsibility, we've introduced a fine system, such as students paying for unfinished meals or plastic waste, or asking for more plastic utensils, with funds supporting to eco-friendly projects.
Our self-sustaining school combines innovation, renewable energy, and sustainable systems to create a healthier environment for learning. This is more than technology. It's about inspiring responsibility and shaping a greener future. By taking action today, we can create a better tomorrow for students and the planet.